Welcome to this lecture series in complex numbers. In this lecture, we'll be looking at the equation of a line in terms of complex numbers. Typically, we study that in coordinate geometry, but one can also do the same thing using the machinery of complex numbers. And let us recall the necessary thing that we need for this lecture. So we studied rotations earlier, and let me recall the main fact. So if W is cos theta plus I sine theta, then we saw that if we have a complex number Z, then ZW is obtained just by rotating Z by the angle theta in the anticlockwise direction. So if we know Z, we can mark out ZW. All right, and let me emphasize that one can think of W not just as rotating a single complex number, but one can think of it as the rotation of the entire complex plane. So suppose I have a line L, and I multiply each point of this line by the complex number W. Then what I would get is the line that is obtained by rotating this line about the origin by the angle theta, right? So we would get, this line where if this is P and that is Q, then the angle between P and Q is theta. So just make a note of that, and with that, let us look at the problems. This is somewhat non-trivial, while the rest two are very easy. And let's get started. So this is the main result of this lecture. Suppose W is a non-zero complex number and R is a real number. Important, R is a real number. Then the set of all the complex numbers Z that satisfy this equation form a straight line. All right. So let's prove this. So first we may assume that the magnitude of W is 1. Why is that? Because if it is not 1, then just multiply both sides by magnitude of W. So on the left side we would get this equation, this expression, and the right side of course becomes 0. So Z satisfies the first equation if and only if it satisfies the second equation, and therefore we may assume that the magnitude of W is 1 because the magnitude of that guy is 1. Okay, so we have that, and now what does this mean? If Z satisfies our equation, then we get twice of real part of W bar Z equals minus R by 2. So since this and that are complex conjugates of each other, the sum is twice of real part of either of them. That is equal to minus R by 2. So let us draw what are the complex numbers Z which satisfy that. Those are precisely the complex number Z which satisfy that. So let us figure out what are the complex numbers that one can feed in here to get that equation, because that will tell us what are all these complex numbers where Z satisfy that, right? So basically W bar Z must lie on this vertical line where this is nothing but minus R by 2. Right, so W bar Z has to lie on this line, and any complex number Z such that W bar Z is on this line must satisfy that. Okay, so we have figured out not the complex number Z's which satisfy this equation. We have figured out the complex numbers W bar Z where Z satisfies that equation. But if we know W bar Z, what do we do to get Z? Suppose W bar Z is here. All we do is we multiply W bar Z with W, which will give us that, which is nothing but 1 times Z, because W bar is mod W square. Mod W square is 1 because mod W is 1. And therefore, to obtain all the complex numbers Z which satisfy this equation, all we need to do is multiply each complex number here with W. But as we saw in the recall, if we multiply, all the complex numbers on a line by W, since W is just rotation by theta, theta is such that W is equal to cis theta, then we get another line basically. So that's it. Since W bar Z's are these, Z's are just rotation by theta of this line. So this distance is that distance, and this is the angle theta where W is equal to cis theta. So that's the proof. That's the completely rigorous and formal proof of it. One could have solved this question by using coordinate geometry. Just write Z as x plus iy, and once you do that, you get an equation You compare real and imaginary parts and you get some equation using x and y, and then you can figure out that that's the equation of a line as in coordinate geometry, and that's it. But I wanted to do it in a more geometric way, and I like this. All right. Now, suppose L is a line in the complex plane. Then we want to show that one can express it in this fashion. So then we want to say that there exist non-zero complex numbers W and a real number R, such that the set of all the complex number Z's which satisfy this equation are precisely the points of L. Right? And this can be done just by reversing this reasoning. Whatever we did here, you can just reverse the steps and get that. So I leave that as an exercise. And now let us look at the perpendicular bisector of two distinct points. So suppose I am given Z0 and Z1 and Z2 rather. So Z1 and Z2 are two distinct points in the complex plane. Then we want to say that the equation of the perpendicular bisector is this. The set of all the Z's which lie on the perpendicular bisector precisely satisfy this equation. So it's very easy. We have Z1 and Z2. So what are the points on the perpendicular bisector? Just by basic geometry, if Z lies on the perpendicular bisector, then the distance between Z and Z1 should be equal to the distance between Z and Z2. And conversely, if Z is such that the distance between Z and Z1 is equal to the distance between Z and Z2, then Z lies on the perpendicular bisector. And this you can prove immediately using a basic congruency. Therefore, the equation of the perpendicular bisector is this. Because the left hand side is this distance and the right hand side is that distance. So that is the equation, but we don't like absolute values, so we square it. Or rather, we don't like magnitude, so I shouldn't call it absolute value. And this gives us Z minus Z1 times Z bar minus Z1 bar equals Z minus Z2 times Z bar minus Z2 bar. And if you just rearrange and everything, then you get that. So that's it. That's the equation of the perpendicular bisector. In the next lecture, I will give some related things as exercises. And with that, I want to end this. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I will see you next time.